This is a brief tutorial on ionic and anionic equations, and this will focus on forming those from the completed reaction. So if you want to talk about completing reactions, look at my chemical reactions video. So there are three ways to write reactions in aqueous solution. There's the molecular equation or formula unit equation, which is probably more appropriate, and it shows all reactants and products in their molecular or ionic form as appropriate. That's how you're likely used to seeing it. So for a reaction between copper and silver, you would get this molecular equation. Silver is in its ionic form, where copper is in its solid elemental form. And you can see the ion with the silver is the nitrate on the reactant side. Although the molecular equation is often used, formula unit equation is probably more appropriate because we're talking about ionic compounds in many of these cases. Now what we ultimately want to do is be able to write the net ionic equation, which shows the ions that participate in the reaction and removes any spectator ions. The spectator ions do not participate in the reaction, but they're going to be necessary to complete the salt. As in the previous example, we have to have nitrate ions to complete the silver nitrate salt, because you can't just go get ions from the stockroom. They have to be in some sort of salt. Spectator ions have to be present in order to complete the salts, but are not changed over the course of the reaction. So they're just kind of hanging out like you're a spectator at some sort of sporting event. You didn't actually play the game, you just sat there and watched. Now to get the ionic equation, we're going to take all the strong electrolytes and write them out in their ionic form. So the ionic equation shows everything in its ionic form. That's a strong electrolyte. Strong electrolytes are your strong acids, your strong bases, and your water-soluble salts. The weak electrolytes, which only partially ionize, and non-electrolytes, which don't ionize, will not be written in an ionic form. The ionic equation then is obtained by eliminating spectator ions, that is, those that are present on both sides of the ionic equation. They'll cancel, leaving us with what's really going on. So let's write and balance the ionic and anionic equations for the reaction of copper metal with silver nitrate, and be sure to include the phase of each reactant and product. So we have copper plus 2 silver nitrates, aqueous, going to cupric nitrate, aqueous, and 2 silvers in the solid phase, so the silver should plate out. Now if we want to ionize that, what are our salts? The silver nitrate and the cupric nitrate. So we split those apart into 2 silver ions and 2 nitrate ions for the silver on the reactant side, and then on the product side we've got a copper ion with a +2 charge and 2 nitrate ions. Those nitrate ions will cancel because they're the spectator ion, and then that leaves us with copper reacting with 2 silver ions to produce copper with a 2+ charge and 2 silver atoms, and that would be the net ionic equation. So let's look at a few examples and write ionic and anionic equations for each, being sure to include the phases of the reactants and products. So if we look at a standard acid-base neutralization, hydrochloric acid and sodium hydroxide, that'll make sodium chloride aqueous and water liquid. So let's form the ionic and net ionic. Everything but the water there is a strong electrolyte. HCl strong acid, sodium hydroxide strong base, sodium chloride water soluble salt. So the ionic equation will have all of that split up. We've got H plus Cl minus plus Na plus OH minus. And on the product side we've got Na plus Cl minus plus the water, which we did not ionize. The sodium and the chloride ions are present on both sides, and so they cancel, leaving us with H plus aqueous plus OH minus aqueous reacting to form water, which is our net ionic equation. Let's look at a different reaction. In this case, we've got barium chloride aqueous plus 2 silver nitrate aqueous, producing barium nitrate aqueous plus 2 silver chlorides solid, because silver chloride is not water soluble. And for an ionic compound to ionize, it's going to have to be soluble. So all of our aqueous salts will ionize. The solid that precipitates, we will not. So we got barium 2 plus aqueous plus 2 chloride minus aqueous plus 2 silver ions aqueous plus 2 nitrate ions aqueous, reacting to form barium 2 plus aqueous plus 2 nitrates aqueous plus 2 silver chloride solids. So what cancels? The bariums and the nitrates, what was in the soluble salt on the product side. And so what's left over? We have 2 chlorides aqueous plus 2 silver ions aqueous going to 2 silver chloride solids. So the precipitation is what's really going on here. But now that I've canceled things, I see I've got a factor of 2 in there, so we'll want to reduce that out. And to say chloride ion plus silver ion, yielding silver chloride solid. So weak electrolytes, non-electrolytes, solids that don't dissolve, in particular salts that don't dissolve, not going to get significant ionization there. There's your gases, any number of different things like that that won't ionize are going to end up in the product equation, which is our net ionic. Now, here is a good example of you can write this, but it's not really going to happen. If we got potassium nitrate plus sodium hydroxide, if I swap the ions in a standard double replacement way, I'd get sodium nitrate and potassium hydroxide. But everything there is a stronger electrolyte, which is a good indication that you're not going to get this type of reaction. There's really nothing that going on. I've just really got a mixture of these two solutions. So you can write this reaction, but really I've just got a mixture of these two solutions. If we work through the ionic and net ionic, you can prove that to yourself, because everything ionizes. You got potassium plus nitrate minus plus sodium plus hydroxide minus on the reactant side. On the product side, you got sodium plus nitrate minus potassium plus hydroxide minus. Everything ionizes, therefore everything's going to cancel, and I've got no net reaction. So really, in that case, if everything ends up canceling, I'd go back and check for weak non-electrolytes, but if that's legitimately the case, you've got no real reaction there. You just have a mixture of the two solutions. Now what happens if we have an acid-base neutralization with phosphoric acid and sodium hydroxide? We need 3 sodium hydroxides to balance it, and we'll get sodium phosphate plus water. Water, again, is a non-electrolyte. But phosphoric acid is a weak acid and is a weak electrolyte, so it's not going to split up either. So we got phosphoric acid aqueous plus 3 sodium ions aqueous plus 3 hydroxide ions aqueous, reacting to form 3 sodium ions aqueous plus phosphate ion aqueous plus 3 waters. So not as much to cancel here. All that cancels is the sodium ion. Nothing else will cancel because our other reactant was a weak electrolyte. So when we write our net ionic equation, we'll get phosphoric acid plus 3 hydroxide ions reacting to form phosphate and 3 waters. And that would be our net ionic equation. So you have to be careful of weak electrolytes in some of these, because they'll sneak up on you and you'll try to ionize it and it's not supposed to. Okay, this has been a brief tutorial of ionic and net ionic reactions.